So hello everybody and welcome to Mathematics of Machine Learning. So from the outset, I would like to say that this particular lecture will be slightly different than the rest in the sense that normally I will be writing as I would be doing on a board, but this one, since it's an overview lecture, I will be using the slides for this. And so for today's lecture, so the main point is really to just give an overview of what we will be doing this year. And so please be muted again and turn your cameras off to save bandwidth. So on this, I mean, if one of you is recording, I think that would be great. So just in case my setup does not work this week. So we're still in the first week, we're still trying out different options and see how they work. Also, if you have any questions, please put them in the chat, and at some points during the lecture, I will take a break and have a look at them and then try to answer, but I will not be answering them immediately. Okay. You don't need to take notes. So sorry, I said that I wouldn't be answering the chat immediately, but I just saw this. There's no need to take notes since everything is on the slides that you will see. And on the recording, and I also have a transcript of what I'm saying here, so there will be no information that will be lost. So there's no need to take notes really here. But normally during other sessions, I mean, it might be advisable even then I will also publish everything, so all the transcripts and all the material that is needed. Okay, so okay, let's begin. So first of all, you can find all the material, everything that's needed here, you can find it online. So on Moodle, but there's also, in addition to Moodle, there's a dedicated website. Let me just show you this, which is, so the dedicated website contains also all the lecture notes as we had before. So pretty much the same material as you will find on Moodle. And it might be a bit more accessible. You will find the slides and the videos, for example, you can find here on the material from what's going on, and even so for the video, you have different formats. So some also putting a copy of the video on YouTube on an unlisted link, so to make it easier to access. So there will also be the exercises here. So for the first week, don't worry, you don't have to do anything. I think for later weeks, so you can so you find information on Moodle in particular. So you can there's a section with assignments where you will be able to submit your solutions, and you will get points for that. But I would say a bit more about this later. Okay, so let's go back to this display here. Okay, so what else? So there are some detailed lecture notes. Okay, maybe I should show you these also, which they contain a higher level of detail than what you find in the lecture itself, and all the additional material. So anything that's in the notes, but that is not contained in the lectures, either the recorded ones or the live ones, will not be strictly examinable, but it certainly contains some additional information or some stuff that can be useful for understanding. So I would really recommend that you read these. So there's also some background information. Sometimes I have some notes and some additional references. So the idea is it's actually a textbook in the making. So if you have some comments on some of the material that is in here on the lecture notes, or if you find some typos or some mistakes, then please let me know. So my plan is to include anyone who contributes some feedback to it into the acknowledgements. Okay, so much for the material. Now let's move on. Okay, so this is the practical information, what I was just talking about. So the online lecture, well, that's the time that we have now. So it's so from 3 to 4 on MS Teams, and there will also be two pre-recorded lectures. Now the pre-recorded lectures, so the timing will not always be that it could be that the online lecture, which is on Thursday, might cover some material that would come before the pre-recorded lectures. So the timing is usually that I'm trying to rather than doing it chronologically, I'm doing it by topics. For example, I'd prefer to use the online lecture more for a certain type of material. Like for example, now so I'm using it for the introductory lecture, which is more of an overview. And next week, I want to use it for a session where we discuss some examples or some more practical aspects. So, but on the whole, it's 3 lectures per week again. And so as I just mentioned, so you have all the material that you need online on 2 different places, 2 different versions of the videos, lecture slides, write-ups, lecture notes. So please try to make use of all the material that's available here. Okay. Tutorials. Okay. So for the tutorials, there will be weekly tutorial supervision classes on Tuesday at 1 p.m. And this will be managed by my teaching assistants there, who are maybe in the audience, maybe not. And so the format will usually be that so for the assignments that you choose, so problem sheet will have 2 or 3 problems marked from which you can choose one, and you write the solution and then you submit it on Moodle. And then so this will be marked, so you can get 3 points per assignment. And then they will be discussed in the problem sessions, in the tutorials. So in the tutorials, you can also ask additional questions or some complementary material. I'm even thinking of maybe using the next tutorial class next week to maybe do a little review of probability theory or some of the basics that will be needed in the course. And again, the plan is to publish some solutions later in the term. So not immediately, but a bit later. And again, so typically problems will be released on Monday and have to be submitted on Monday. Okay. Now, the next topic that I get commonly, I get asked quite a bit about prerequisites. Some people seem to be worried about, okay, I'm making my video a bit smaller, so I think that should be better. So again, this is a common question, as I just mentioned. But in essence, the core material from the first 2 years should be enough. So the course requires a certain sophistication with linear algebra and with probability theory. So you should be, you should not really be struggling when it comes to linear maps and matrices, and also when dealing with probabilities and expectations. But there's some material online that you can refresh on this. Other than that, there's not really much that is being required. I mean, occasionally I will use the notion of a metric, but you don't really need to have taken metric spaces for this. So the mathematics is mostly really based on what has been done in the first 2 years. And I put some documents online that can help you review some material. So oh, there's a typo here. Okay, sorry about that. So they can help you. So these prerequisite materials that I put online, they usually contain a lot more information than what you will probably need. So you can simply scan through them as a type of refresher. Okay, but don't worry too much about prerequisites, since if there's anything really that I think that is not part of what has been done in the first 2 years, then so I can spend some time on reviewing that part. And actually in today's lecture, I want to spend some time on reviewing some notions from probability theory. Okay, so what else? Again, so depending on need, we can also use tutorial classes maybe for these kind of things. Okay, so computing. Machine learning is inherently linked to computation. So as this course is mainly on the mathematical foundations, however, so no specific prerequisites are assumed on this. I would nevertheless encourage you to learn some Python programming simply to complement this lecture. So it's not strictly needed, but if you have the opportunity to, then please try to get into some computational things. So it will certainly add value to what you learn here and give you the opportunity to turn the theory into practice and also to try out some things. So I will occasionally use some code for demonstrations, and the idea is also to publish this code. So to publish it on Moodle and on the website. And there are some specific links here that, so if you want to learn more about things, so this is usually the setup that I use. So Python is a programming language, but it comes in distribution. So you can download a certain package that contains the programming language and all the tools that you need. And the one that's commonly being used is Anaconda Python. Certainly you can also use MATLAB if you like, right? There's also this machine learning package, scikit-learn and PyTorch, or there's also TensorFlow or Keras for those of you who know about this. And so I would really encourage you to experiment. I mean, there are very detailed tutorials about these pieces of software, and but this is not the main focus of this course. So the focus here is on the mathematical foundations, but that will give you the basis to understand all the algorithms and methods that you might end up using depending on what you choose to do afterwards. Okay, so far, are there any questions? So I will just go through the chat now before I continue with the material. So let me just see. Okay, so you can. Someone was okay. Yes, so the first problem sheet has been released, but it is not assessed. And I should mention, so there was a small mistake there in the sense that I originally accidentally published a previous version of the first problem sheet, so one that wasn't ready yet. So the website and Moodle said that it will not be assessed, but on the sheet itself, it said that you should hand in question 1 or 2 or 3 or so. And but I changed this, I think. I believe that the current version should be the correct one. So let me just check briefly. So it's the exercises problem sheet. Yes, so that's the current version. It will not be assessed. So this is just as a warm-up, right? I would still recommend that you try to work on it, okay? But this is just to get you going with some of the notions of probability that will be needed, or that will make an appearance later on, okay? Okay, so let's go back to the lecture. And so, okay, so there's, what are the comments? Beginner exercises and gamer moment. Is it okay to just know the most basic fundamentals of Python? Yes, I mean, it's, again, so it's not really difficult, and as I just mentioned, it's not needed for this lecture. I mean, it's absolutely not needed, but it certainly adds value to it. So you should definitely complement this course, which is on the foundations of machine learning, and which explains you why the algorithms work and things like that. So it's certainly helpful to complement it with Python, but learning Python is rather easy if you know some other programming language. So it's the same as with languages. So if you speak Spanish, then you can easily learn Italian or so. So if you know MATLAB fairly well, then you can easily learn Python, right? So more or less, unless it's a completely different language, but that's another story. Okay, so what else? Yes, someone is taking personal recordings. That's good. So the seminars, how will they be structured? So the idea is to have them. I mean, this is really then partly also up to the teaching assistants, but so part of it will be answering questions or giving some advice or help with some of the problems that need to be solved for the next week. And part of it will be discussing the solutions to previous year's questions. So it's essentially like you would have in supervision classes, essentially. But if there's something that needs to be clarified a bit further, you can also raise it, and so it's pretty flexible, right? Yes. Anything else? Should we watch the pre-recorded lectures before attending the live lecture? It depends really on the, so whether they cover material that comes before or after. So all the lectures, the recorded ones and the live lectures, they all have numbers. So in this case, so for example, today, this is the lecture number 1, and then the pre-recorded lectures are number 2 and 3. So this means that technically this one comes first. Now, because it's the first week, and since this lecture is really just an overview, you could have started, or many of you did, looking at the pre-recorded lectures already, and you would be able to follow them without this particular one here. And in any case, even for the live lecture, the plan is really to release the material for it, or the beforehand. But ideally, normally the plan will be to have the pre-recorded lectures come before this one, simply because the live lecture is on Thursday, so which is towards the end of the week, and to have the pre-recorded lectures come before that. And in that sense, yes, so you should look at them beforehand. Okay. Also, but again, so as I mentioned, so the plan is to publish the material simultaneously at the beginning of the week for the whole week, and sometimes also the content will be independent, so it will not always depend on each other. So in some cases, if you skip one, it's not that bad. Okay, so that's it for the questions for the moment. So let me then go back to the actual lecture material. So, okay, so now we discussed the prerequisites, and now we will begin with the content of what we will be doing. Okay, so the first question is, what is machine learning really? And then to go back to the more basic question, what is learning? And so learning can be seen as the process of turning experience into knowledge. So, right, you experience something, you see something, and you turn it into knowledge, and then into, and a machine learning is essentially when a computer does that, right? So it's a branch of artificial intelligence, if you like, but traditionally artificial intelligence has been rule-based. So you told a computer exactly what to do. If A happens, then do B, and so on. But this turns to be too complicated. So machine learning takes a different approach. So it actually lets the computer learn on its own the way a human would be learning, and basically from experience, right? And it could be supervised or unsupervised learning. So we'll come to that in a minute. And so the next question is, how do we measure knowledge, or how do we know that an AI knows something? And essentially it's by what it can do with it. So knowledge is measured by what you can do with it. So for some specific tasks in machine learning are classification and pattern recognition, ranking, clustering, regression, decision support. And so did I mention prediction? That goes under regression, or even playing games. I mean, that's so something that if a machine is successful with that, so you would assume that it has gained some knowledge or something. And the examples that we will be studying at the beginning would be mostly classification and pattern recognition in a sense. And so the next question is also what can be learned, and how do we assess the results of a learning process, and how efficiently can we learn a task? And these are all the types of questions that we will be looking at in this module. And we will be studying this from the point of view of approximation theory, of statistics, and in particular statistical learning theory, which will make up a big part of this module, and optimization. So we will then also look at many concrete case studies in the final part of this module, when we look at selected topics in deep learning. And that will actually bring us to the frontier of current research in the field. But so we start with the basics and look at the different aspects that we mentioned here: approximation theory, statistics, and optimization. Okay. So first things first. So in machine learning, the goal is mathematically, you can formalize it as trying to learn a function, right? So a function takes inputs, some input space x, and it does something to it and assigns inputs to outputs, and the inputs are usually called features in many cases. So the formal setting is where you have some, and the elements of the output space are called labels or response. If it's so it could be a discrete set, like in the case of digits, for example, it could consist of the digits 0 to 9, or it could consist of 0 and 1, or yes and no, if you have a binary classification task. And here's a classic example that's often used as a benchmark for machine learning problems is digit recognition, right? So what the input space consists simply of images of a certain size. And these are simply points, pixels, or whatever. And then the output consists of a digit. And the idea is that you give it an image, and H tells you what it is. It tells you that this is a 4, that this is a 1, this is a 9, and so on. Okay. So that's the basic problem, is really to find such a function that does well, and we will just discuss in a minute what it means to do well, and how do we know whether a function that we came up with actually does its job without having to evaluate it by hand. Like in this case, we could simply evaluate it by hand, right? So we could simply give it a bunch of these images, and then we could say, okay, it did well on most of them, but how can we evaluate the performance of such a classifier without simply looking at it by hand? Okay, because otherwise we could just do the job ourselves. Okay, so there's roughly 2 types of learning. And so one is unsupervised learning. So this is when we do not have any information about the data, but we try to figure out something about the data. For example, clustering, right? So we see this bunch of points, and then we see, okay, so they could be coming from 3 different sources, and we try to then separate them into 3 different parts. So the green, blue, and red part. Okay, so this is an example of what's called clustering. Simply trying to figure out differences in the data just by looking at it, or having a computer look at it. Then there's the idea with supervised learning, which is more like the way children would be learning. So you give some sample data, okay, in some supervised learning. So where we have some training data, that's what it's usually called. And this consists simply of pairs of inputs and outputs, and the corresponding outputs, and the goal is then to generalize. So you look at a sequence of input and output pairs, and then the goal is to infer some kind of relationship between the input and the output so that we can make meaningful predictions on unseen data. For example, I could use a collection of images and digits to train a classifier that would take an image and tell us which digit it represents. And then I could expect that a classifier ideally would correctly guess the digit represented by a new image that it has not seen previously. So essentially, it learns from training data that is given to it. And most of the common applications of machine learning, such as natural language processing and voice recognition, are examples of supervised learning, right? So you speak to your computer, and then it kind of learns to recognize your voice so that it can recognize it the next time around. Okay, and now, so one can view learning really also as a problem of function approximation. So you can think of some relationship that maps inputs to outputs, or that assigns labels to some inputs image, for example, and some relationship that generates the data. But then, could you please mute? Sorry, is there an issue, or? Okay, is there, sorry? Oh, is my sound off? Oh, did I mute myself? Did I? Let me check. Is it? Okay, so why? So now it's okay, right? Can you hear me now? Okay, so was I muted the whole time? Okay. Oh yes, sorry. So I wasn't monitoring the chat, so that's good that someone, that's kind of strange that I kind of got muted automatically. Okay, so let me just go back and just look at the chat. Oh, okay. Yes. Okay, so I will just briefly run through this now. Just a second. Just in case you missed something, you probably didn't miss anything, but so I was just saying that it's a machine learning. So again, so you have some inputs, which are images. There could be images, could be anything else, and you have some space of outputs or labels, and then so you try to assign an image to a label, and then you have the idea of, am I? Yeah. Okay. Sorry about that. I should. I'm going to look at the chat more often now. Okay. So I have it. Actually, I have 3 devices here, so I can use one for the chat. Okay. So that's good. Thanks for pointing this out. But I hope so you get the message here that we try to guess a function that does something meaningful, right? So it recognizes a digit, for example. And then we have this idea of unsupervised learning, so where we try to learn some relationship in the data without having anything to learn it from or any training data. So we try to guess, for example, that this data, this bunch of points might be coming from 3 different sources, which are here illustrated, and we try to figure this out, which part of this comes from which source. And then in supervised learning, we have some, so that would be correspond more to the way that the children learn. So we have some combination of inputs and outputs, so something that will guide us, and then we try to generalize. So the problem is then to construct a function based on this information that we have, and that would take something unseen, an unseen input, and assign it to an output. And so we can also think of it from the perspective of approximation theory. So we can think that there's some true function, some true underlying function f that does something, that assigns some images to some digits, for example, or anything else. And then we can try to approximate this function with a function h from a given class of functions. So we don't know what f is, but we see some input-output pairs, and then we try to find a function f from a bag h. So I usually like to think of my function h as being a bag of functions that I can grab some functions from, and then to find one that kind of best fits the data in a way. And examples are, for example, indicator functions, functions that give you 1 or 0, or linear functions for linear regressions, or polynomials, or so a certain class of functions that are called neural networks that we will be discussing in some detail. Okay, and now exactly what kind of functions to choose, it depends on different factors. So it can depend on considerations of computational complexity. So if I have very complex functions, it might be very difficult to find them. It might depend on statistical considerations. So maybe a simple function would be enough to describe the data, but it also depends on the complexity of the problem, really. And so we can look at an example. So this is a particularly simple problem that you may have seen in statistics or in probability theory for those of you, but otherwise it's not, if you haven't seen it, well, so probably anyone has seen something like this. So the idea is that you have some points, some pairs, say x values, which are here drawn on the x-axis, and y values, corresponding y values. And if you look at the data, it looks roughly like they're roughly linear with some noise. Okay, so one approach maybe would be to approximate this relationship by a linear function. And here you have a function of this form. Now, in this particular example, it depends only on one x value, but in general, you can have more factors. And then, so you approximate the data that you see by a linear relationship. And then when you see a new data point, you just plug it into this linear equation and you get a prediction, right? And the prediction will be on this line. Okay, so that's a very basic example. So this has been studied by, linear regression. This goes as far back as probably Gauss, when beginning of the 19th century, when he invented linear least squares or linear regression to predict the orbit of the Jupiter-Moon series, and that's one of the things that made him famous. But for many other tasks, however, this method is not sufficiently flexible, so you might need a more complicated relationship. Okay, so one of the models used for more complicated relationships is that of a neural network. So this is usually depicted something like this. And mathematically, you would simply describe it as a function that is a composition of simpler functions. So one of these functions would be a linear function. So you alternate between a linear function and an activation function. So don't worry about the details. So we will discuss this in great detail later in this course. But the idea is that going from one level to the next is usually simply applying a linear function and then applying some activation and then again. So this is more or less inspired by the architecture of the brain. So when neurons fire, this means that you get a connection from one neuron to the next. So that's why it's called neural networks. But nowadays, the models from them don't have much in common with biology. So it's simply a model of functions, of nonlinear functions that can do a lot of things and have been successfully used. Okay, and then, so neural networks, they have plenty of applications. So there are countless applications there. In natural language processing, that's one of the most common ones. In medical diagnostics, so you could give it some samples and then say, I can tell you something about the disease. Self-driving cars, anomaly detection, when you try to detect earthquakes, for example, or some anomaly in financial data, voice recognition, financial forecasting, medical imaging, drug discovery, manufacturing, or even generating realistic data like a deep fake. So you can generate images that look like they would be images of real people, or text that looks like it might have come from some person. You can generate music artificially. You can have it play games. There's even an interesting one that I discovered recently, which is the IMO Grand Challenge, which is the problem. Okay, so this is here they're actually trying to build an artificial intelligence system that would compete at the International Mathematics Olympics against humans and see how it goes. So yeah, let's see how that works out. I mean, there's so some of the more famous examples are AlphaZero. So this is like a neural network that learned to play chess from scratch and beats every human. Or here's an example that I've been looking at lately, which is related to drug discovery. So there are plenty of examples really here. So why is it called neural network? Someone has asked. Again, because this more or less resembles the structure that neurons are connected in the brain. But I think this has historical reasons. So nowadays it's not really that attached to the biological motivation anymore. Okay, so the question is now, we saw two extreme examples. So we saw linear functions, which were very simple functions as a class of functions to approximate an input-output relationship. And we saw neural networks, which can do pretty much everything. So what can we say in theory really about how good we can approximate a function or something using a certain model? And okay, so since this module is about mathematical foundations, so we will study the scope and limitations of learning procedures. And for example, what can be learned in principle? And so there's an very old result from the 19th century in approximation theory, which tells us that in principle, any continuous function on an interval can be approximated to arbitrary precision by a polynomial. Now, why is this good? Because polynomials can be represented on a computer efficiently. So you just have to list all the coefficients of your polynomial, right? If you try to approximate something with a quadratic function, you need 3 coefficients, A, B, and C. And so you can find the 3 coefficients that represent a quadratic function that best fits your data, for example. Now, so the problem with this result is that it's not constructive. So it does not give you a method of actually constructing such a polynomial. And so it also does not give you an efficient procedure Well, that's what I just said, but it also does not give you any control on the size of the approximating polynomial. For example, it could be of massively huge degree. Okay, and so these results are in that not particularly, they are certainly interesting, but not particularly useful in practice. Okay, so but there are many variations of this result. For example, there are similar results for neural networks, and this is one that we will prove in this lecture. And this is due to Sibenko, I think it's from the 1980s. And it tells us that if we have a continuous function interval, then we can approximate it to arbitrary precision using a neural network. And even a neural network with only one layer, that would be enough. And this is quite nice because neural networks, they can be found through training. So this is something that we will discuss also in this lecture. And training can be carried out relatively efficiently using backpropagation and algorithms such as stochastic gradient descent. And there are also many variations of this result that can give you bounds, say, on the say the size of the network or the complexity of it. Okay. Now this brings us to the next point of view, namely how to actually find these functions. I mean, we have seen that you can approximate any function with such a neural network, but how do we find one? And this brings us now to the concept of training, actually. And and this brings us to the perspective of optimization. So optimization is usually the art or maybe science of making optimal choices. And in a mathematical setting, really optimization is about minimizing a function. So you try to find a minimum of a function. That's it. Now here, the function that we would like to minimize is called the loss function. So the loss function, so what does it do? So it kind of penalizes the mismatch between a prediction and the true value that we would like to have predicted. Right? So if we have training data, for example, then we have an input xi, we have an output yi, that's what the output should be. But then we also have a prediction on xi when we apply a function h to xi. And then we want to know, is this predicted value the same as this seen output here, or is it not? Okay. And so how do we measure it? Well, we have a loss function. So a loss function takes, again, so it takes the output of our prediction engine here, of our classifier, and it takes y, I, and it gives me a large value if this is, if these two are different, and a small value if they're the same. So, for example, what is, okay, so the average value of this loss function on all the training data that I have, this is what's called the empirical risk. Okay, and the goal is then to minimize this over a certain class of functions. So to find a class of functions that minimizes this empirical risk. So to make a bit more sense of this, let's look at some examples of what a loss function might look like. So you might think of a loss function as, so for example, this is called the quadratic loss. So it's simply the difference between a value y and the function value at x. So of course, if these two are different, then this will be large. If they're the same, then this will be 0. And this is the setting used in regression, for example. Or the binary loss. So this is typically used in classification. This gives you the value 1 if the predicted value is not equal to what it should be, and 0 otherwise. So for example, if we have, let's take the example of digit classification, right? So X is an image, and say it represents the number 9, and Y is then the number 9, really, and then, so I come up with a function that takes this image, but says that this image represents a 3, for example. Then this function will be 1, because it was a miss. Oh, sorry, there's a mistake there. Should be the other way around. It should be 1, and this should be a y. I should have checked my slides. Apologies for that. I will fix this before and upload a corrected version. So this is the indicator function for h of x being not equal to y. It should be 1 if they're different, okay, and 0 if they're the same, okay. And the logistic loss, this is something, don't worry about it at the moment, we will look at it later, okay. Okay, so again, so we want to minimize this function. So in the case, for example, of the unit loss, where this is the indicator function, so every time I get something wrong, this will add a value of 1 to it. So if I get everything wrong, this whole risk will be 1. If I get everything right, it will be 0, okay. And I try to find the function that works best for this. Now, there's this idea that in principle, so I could simply, so it depends on the class of functions, how small I can get this. For example, if I only restrict to certain linear functions here, then I might have a big loss. But if I allow any function, I could simply learn by memorizing, right? So I could simply define a function that simply is defined as taking the value yi on xi and an arbitrary value otherwise. So that would be a function that has 0 loss on the training data. But I think we can agree that this is not a very useful function, right? So why is this not a very useful function? Because it does not tell me anything about data that I have not seen yet, okay? So we want to actually construct functions that work on data that we have not seen yet. And for this, to really make sense of this idea, we have to analyze, so we have to go a bit into statistics. So we have to, and for that, I will just recall quickly some concepts from probability. So before going on, and so much of it should be familiar to you. Otherwise, again, here's a quick review. So we can talk about the probability of some events. A, for example, rolling a die, and if I say that the event is that the result is an even number, that would be an event. Then we have random variables, which can take certain values. And I could say probably if x, for example, represents the result of rolling a die, so then it would be a number between 1 and 6, and a could be the event that it's an even number, and then this is the probability that the result will be an even number, for example. And again, so a random variable can be discrete, so it can take only finitely or countably many values, or it could be continuous, right? In the discrete case, statements such as the probability that x is equal to k makes sense. In the continuous case, you don't have this, but so you have a density, okay? And so this density is simply something that you can integrate over. So the probability that x is in A would then be the integral over A. Okay. So I hope that this is not completely new to you. Then there's also the notion of an expected value or mean, which is simply taking the average value. So simply taking all, summing all the possible values that your random variable can take, weight by their probability. Or in the continuous case, you replace the sum by an integral. Okay. Now, so maybe the more tricky or more important part here is the notion of conditional probability. And so this might not be as standard as it should be. So in the case of a discrete distribution, so the probability of x having a certain value of small x, given that y has value small y, is the probability of x being small x if we know that y has been observed and has the value small y. So we simply condition on something having happened, and this can be written as the ratio of the joint probability of x being small x and y being small y divided by the marginal probability of big Y being small y. Now, if x and y are independent, so this means that y does not give you any information about x, then in this case, this is the same as the probability that x is equal to x, because it does not really, it's not affected by y. And I would really encourage you to think about these concepts in a more in an intuitive way rather than in an overly formal way, right? So if you read this, then just think of it in an intuitive way. The probability of x being small x, given that you know that big Y has the value small y, okay? And now, and here's an example. So I will not dwell on it too much, but this is related to what I just said before. And so, by the way, if you're not too familiar, again, so there's the additional material that I published on the website, so that should give you a refresher on these concepts. And of course, these concepts also work in the case of continuous distributions. You just replace the probability with a density. Okay. And now there's the notion of conditional expectation now, and this is slightly more tricky. Okay, so again, so we illustrate this using discrete distributions to make it simpler. So the expectation of x, given that y has a certain value y, well, that's simply the same as you would define the expectation of x, but just instead of just taking the probability that x is equal to small x, you take the conditional probability under the assumption that you know that y has the value y. Okay, and again, in the continuous case, you have an integral, so it's the same. And now, so what is this here? So the expected value of x given y is itself a random variable, and it takes these values here. So it takes these conditional expectations as values. And then you have the rule of iterated. So this is a random variable itself, so this quantity here. And there's the rule of the iterated expectation, which means that if you take this random variable and take its expectation, it's the same as the expectation of x. Okay, so here you find a quick derivation, but the interpretation is quite simple. So you simply think of the expectation as an average, right? And you first average over x. So for each conditioned on each particular value that y can take, and then you average over all the values that y can take, which is the second expectation. And then so you have the average over x. Or you can simply think of it as if you have your data, right? And depending on the values that y takes, you subdivide all the possible things that x can be, and then you average each of these groups, and then you average over the whole group. Okay, so that's in essence the point. So that's really it. Okay, so now I think I have to hurry up slightly, but we're almost there. So we now look at the concept of generalization error, right? So rather than taking as before the average over training data of our loss function applied to h, we take the expected value over the whole data space. So we assume that we have a probability distribution on our whole data space, x and y. And this is what we call our data generating process. So this is how our data is being generated. So we could think of it like as a function mapping x to y plus some noise, for example. And then we look at the risk over the whole data space, the expected value, rather than just the average over the training data. Okay. And now, of course, if the input-output pairs are itself random, if they're independent and randomly taken from our space, then the expected value of this is equal to this. So we can think of this as being an estimator for this using statistical language. Okay. And ideally, we want this to be small, right? So we want this quantity here to be small. And we will see that there are ways of actually bounding this quantity, and we will study them. Okay, so finally, let's come to the last point, or one of the last points here. And this is the idea of, say, learning versus fitting, right? So suppose that our data follows this rule here. So the orange curve is our data generating process, and we have points that we sample which are taken from around this curve with some noise. Now we could try to fit this with linear functions. Wouldn't work too well. Then if we can use polynomials of arbitrary high degree, then we can actually find a fitted model or a function that actually goes through every one of these points. So it works perfectly well on the training data, but it's completely useless to predict anything. So if I sample a point here that is around this curve, the blue curve will tell me that it's way down there. So it's completely useless. So this means that having this flexibility of being able to choose arbitrary or polynomials of arbitrary high degree does not really help us a lot here. I mean, so we can fit the training data perfectly well, but we are nowhere near in modeling this actual data generating process. Now here in the middle, what we see is a kind of like a compromise. So this is when we put some restrictions on the type of functions that we are allowed to choose. So we say we are only allowed to choose polynomials of small degree. Then we can do actually a very good job at approximating this orange function. So this is a bit strange because so what this means is that more flexibility in is not necessarily a good thing in this case. Like here the training data is not here we have some small mistake on the training data. So if we compute the empirical risk function here on the training data, then it will not be 0. There will be a small mistake, but this function will work very well on unseen data. Okay, so this is a trade-off between estimation and approximation that we will study in some detail, because this is so at first sight this might be a bit counterintuitive. Okay, but so we can also interpret this that here we are not only fitting the data but also the error that's included, and this is what's called overfitting. So this is a common problem in statistics and machine learning. So and we will study this phenomenon in a bit more detail. Okay, so I have 2 more slides, but I will probably, I mean, they're not so crucial at the moment, so I will skip them. I would just like to mention something about optimization. So in practice, our functions will be parameterized, like in the case of linear functions, it's the coefficients that we have. And we try to minimize this by minimizing a function of the coefficients of these functions here. And then typically each of these functions is a sum. So for every data point that you have a term here. So it's a function of this form. It's a function that is a sum of a large amount of functions, possibly millions of them. So if you try to compute with them, if you try to put them into your computer and compute gradients and try to minimize these functions, that can be hopeless. So the idea is then to use some stochastic methods which just choose a few of these terms randomly, compute the gradient, subtract it. So you start with an initial guess and then you do different iteration steps, always subtracting the gradient of your function until you arrive at a minimizer. And so it turns out that this works. So this method is called stochastic gradient descent. So we'll discuss this in quite some detail. This is the standard method in deep learning for finding or for fitting neural networks to data. And so we will discuss this also in quite some detail. Okay, so now to summarize, and apologies for being a few minutes late. So this course will consist of 3 parts. So the first one is statistical learning theory, where we will study the trade-off between approximation and estimation, for example, in some detail. Then the middle part will consist of optimization. So we will discuss methods for minimizing functions, and we will discuss stochastic gradient descent and also some applications like support vector machines. And then the last part is where we will be moving closer to more very current research on deep learning and particular neural networks and their different variations and applications of them. Hopefully, we also get to look at some reinforcement learning and also on models for generating data. Okay, so thank you very much. And now I can take some, that's all for today. And now I'm happy to take some questions if you have some, but I will first check the chat to see if there are some. Okay, so any questions, or maybe I can put up the volume. So if you, but it's probably best if you, so apologies for being a bit, Okay, so unsupervised learning, does it make predictions or only find patterns? So it's actually mainly for finding patterns like clustering, but it can be used in combination. It can be used to make predictions, for example. Say if you have a clustering problem, and we will be looking at one example of this it's actually in one of the recorded lectures that it's the one on binary classification really, so where we discuss what's called a Gaussian mixture model. So you have 2, say, data sources that are mixed, right? And you try to separate them. So in fact, so trying to separate these two, that can be a problem of unsupervised learning. So you simply look at your data and then you say, okay, this sample comes from that source, that sample comes from this source, right? So in the lecture notes, I'm discussing this with an example from house prices from different towns, for example. And then you try to look at the prices and figure out from which town they come. So that's an unsupervised learning problem. But then, so once you solve this unsupervised learning problem and you can use it then also to make predictions. So if new data comes in, you can use it to assign it to one of the two groups. So they're usually connected. So each part of the course, so I plan to make them roughly same length. So the plan at the moment is to take about 9 lectures for each part. It's so 9 or 10. That's by design. I mean, there might be some variation, but I really try to keep them the same, more or less. Okay. Anything else? Okay, I think we are. So the good thing is that you don't have to run to other buildings now, maybe. And then, okay, so if you have any more questions, then okay, is there anyone? Oh, so I didn't check if there were people raising hands or so. So recommend in terms of asking questions, just simply type them in the chat, right? So rather than anything else, and then so I can address them from there. Okay. So I guess that's it for now. If you have any, or is there anything more? Let me check. Okay. Yep. How are the assignments marked? Yes. So you will get 3 points. So you get a total of each assignment sheet will count 3 points towards the 15 points that you can get in maximal. That because so the idea is that the assignment should make 15% of the end mark, with the rest coming from the exam. So if you have 5 assignments, and the idea is to have 6 assignments that are being marked, and each one of them can give you 3 points. So you can certainly get more than that, but you have a chance of getting, if you get more than 15 points, it will be capped at 15. Yeah, so each of them will give you 3 points. Okay. Anything else? Okay, so you can always reach me again. So apologies for rushing a bit, but you can find all the materials. Hopefully the recording has worked out. And so thank you for your attention, and I see you then next time around.